In this first lesson on limits, we're going to meet three goals actually. They're 1.2, whoops, sorry, 1.2, 1.3, 1.4 in our list of things from College Board that we need to cover. We're going to, 1.2 is defining limits using limit notation, so we're going to use some notation. 1.3 is estimating limit values from graphs. That word estimating is really important. And also estimating limit values from tables. All right, so we're basically going to do notation, what I call tabular and graphical limits. So we'll start off with the notation. First, we're going to tie it in pre-calculus and calculus. All right, so up here I have what's called a rational function. So with a rational function, it's basically a function over a polynomial over a polynomial, to be exact. But the coordinates have there's a hole in the graph at -3, 7, 6. So right here in this guy, we're at -3, comma, 7, 6. So the function isn't defined at -3. But you'll notice a few things about it when we start talking about limits. So let's go down here a little bit. Let's talk about pre-calculus. As x heads towards -infinity, so really what you do is you hop on this road, right? And you move x towards -infinity. So my x is shrinking and shrinking and shrinking. And the question is, what is f of x, which again is really the y, what are the y values approaching as I approach -infinity? And you'll see that we've got a little horizontal asymptote up there at 2, and they're approaching 2. Now, using limit notation, we'd say the limit as x approaches -infinity of the function. That's really important. A lot of times I see students leave that off, and that's like leaving the subject off of a sentence in English class. You'd never say the barked. You would say the dog barked. And you'd never say the limit equals 7. It's like the limit of what? And we'll be having multiple functions in a singular problem in this class. So it's really important that you get that subject on there, and you will be docked for what we call notational fluency if you do not have it. Okay, so we are up there at 2. All right, next up, as x approaches positive infinity. And again, you can hop on the road wherever you want, but as we go to positive infinity, we're going to be heading in this direction. You'll notice that the y's are approaching 2 again. So we'd say the limit as x is approaching infinity, as I go forever along the x-axis and I'm charting my y values, which are f of x, they are clearly approaching 2. Now again, it says estimate because maybe it's 2.0001. So you know, you do your best. As x is approaching -3, okay, well, from which direction? In words, it said from the left. So as we approach -3 from the left, our y value, or our f of x, is up there at the y value of the location of the hole. So that was told to me as 7/6. So 7/6. As we approached from the right, it's also at 7/6. Both roads are leading to the exact same open dot. So although the function itself, the y value, doesn't exist at -3, the limit does. Because although there's an open dot there, I am there when I come in from the left and I come in from the right. And to write that, we'd say the limit as x approaches -3 from the left is with a little minus. Don't read that as being negative. It means from the left. Okay, we can approach 1,000,000 from the left and we'll be very positive. All right, so be careful with that. My subject is still f of x, and I was up there at 7/6. Similarly, the limit as x approaches -3 from the right is a little positive sign, or a little plus sign, but it means you're coming at it from the right. We were also at 7/6. All right, now you go take a look, maybe pause this video, and you approach 3 from the left and write it. So do it on the graph. Go walk the road, all right, as you're approaching 3 from the left-hand side. So we are going to approach 3 from the left-hand side. Let me grab my little highlighting tool here. So we'll approach 3. From the right-hand side, we're heading here. We jump the hole, we head down here, but our x's are going to the right. We can't get past that vertical asymptote, but as we get closer and closer to -3, we are going to continue to get closer and closer to -infinity. So we would say the limit as x is approaching 3 from the left-hand side of the function is equal to -infinity. And likewise, from the right, it's going to +infinity. So if we go back up here and approach 3, we will be heading towards +infinity. And I should have said approach 3 from the right. And you go ahead and you write that in. So it says, based on what you've just seen, how might you informally define what the value of a limit represents in terms of the graph? Well, what is that value of the limit representing? It is the y value. So when we talk about a limit, we're talking about a y value. It's the limit of a function, f of x, g of x, h of x, which is the y value, or what we would call the dependent value. It is the y value that we arrive at. That's not the best definition, but it's said informally. So back to that same rational function right here. It says complete the table. Now this is going to require a calculator, so you might want to pause this and either go grab a TI-84 or Desmos, or so I use the 84 on my app, so we'll go do that. So, but we're going to set it first. Okay, so what I want you to do on your calculator, once you find it and you've paused this video, is when you're making a table of values there where there's these x values that are sort of, I guess what you'd say all over the place. Let's go take a look. First of all, I want you to hit your mode button. Make sure we're all lined up there on the left. We are always in radian mode in this class, so make sure that's ready to go. The second thing, we're going to make a table. Go to the table set, and here's something you might not know, is the independent variable, or the x, I'm going to set to ask, and I'm going to hit enter. What it'll allow me to do is make a very specific table for these specific x values. I don't have to like scroll to 1,000. And we'll leave the dependent variable, which is the y, or in this case the f of x, on auto. All right, so once that's set up, we are going to go to our table and we're going to go look at it. But before we do that, we have to enter our f of x, or our y, equals. Rational functions need to be locked and loaded in parentheses. So we've got our 2x squared plus 5x minus 3, parenthesized, divided by, parentheses, x squared minus 9. Now, as we move through the chapter, you're going to be able to approach this much differently and not be estimating using tables and graphs. You'll be doing it exactly using algebra. So I've got my rational function f of x entered in there correctly. So you might say, why does she keep saying rational function? Why does it matter? I'll tell you a little story. So the third year I was teaching calculus, kids came back after taking the BC exam, which is the Calc 2 test. And they're like, what's a rational function? It said that we're to write our answer as a rational function. I said, you guys, it's just a polynomial over a polynomial. And they're like, oh! And they had the skills to do that. They just didn't understand the vocabulary, and it was all my fault because I just said the function f of x. I didn't say the rational function. So they didn't get used to that vocabulary. So sometimes if you see me, if you hear me repeating something over and over again, I'm doing it intentionally to embed it in that long-term memory of yours. So let's go take a look at our table, shall we? So let's go to table. All right, and it's weird being back up here. This is my first set of notes that I've done on my smartboard since we got out of school in March. So I'm like, if I bumble around, you guys will forgive me, right? So let's go enter those x values. I believe they started at, yep, they went -1,000, -500, -100, let me see if I can remember that now. -1,000, enter, -500, enter. It was negative 100, enter, and then I forgot. Was it negative 50 and then 50? Let's see if I can slide, yeah, negative 50, 50, and then symmetrically there. So negative 50 and 50 and 100. Oh, isn't this fun? And 1,000. As a year goes by, I'd normally just say go create your table, but I wanted to show you that table set. So you should go write those values in here. We are at 1 point. I'm going to see if I can get a copy so I don't have to keep flipping. Just a second. I'm going to go to my master set of notes here and see if I don't have that already written down so I don't have to keep flip-flopping back and forth. I do. All right. Because we're going to be using this exact same function quite a bit. I don't have to keep going back and forth with the calculator. I'm sure you don't want me to have to either. So let's go back here. Let's load that up and let's go enter them. It was 1.995. And we always round to a minimum of 3 decimal places in here. That might be a question I ask just to make sure that you're listening to the notes, but it's a College Board sort of standard rule is that we round to a minimum of 3 decimal places. 5, 1, and then 1.906. And then at 50, 2.106. And then at 100, 2.052. And hopefully you did this on your own calculator because the other ones, I'm going to assume you did this first one and then we're just going to write them down for the next ones just to save ourselves some time because that certainly wasn't very exciting. But based on what I'm seeing here, what is my limit as I approach negative infinity? So I'm heading this way and I'm looking at what this is trending towards. If I were to give you $1 million, if you guessed it right, I'd hope you'd guesstimate too. That's why it's called estimating using tables and graphs. It might not be. It actually definitively is because if you think about it, as we approach the infinities, the y values of a graph give us the horizontal asymptotes, the limiting value up there. And you should have been taught in pre-calculus that when you're looking for horizontal asymptotes, it's all about where that highest power is. Some people teach like a biggest on denominator 0, so like I think they call it a Bodo, something, 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 I don't know. We're going to use it as analyzing. We're going to do it a little differently in here, but you should have been taught that if the powers match, you steal the ratio of the coefficients. And notice I get a 2 there. So that isn't just a guesstimate. I know that's 2. Same here. When I approach positive infinity, I've got these same type exponents. So I'm going to steal those coefficients. And it shouldn't be a surprise that I'm going to guess that as I go to positive infinity, that is also collapsing towards 2. It's a guess off my table. So tables are the worst way to do limits. The algebra of it's going to be the best. So how is the numerical analysis above related to the graph of the function? The limits as I approach the infinities gave me the horizontal asymptotes of the graph. Okay, as I went to infinity, my limit was 2, horizontal asymptote at 2. As I went to negative infinity, and you can write that down yourself. All right, so same function, f of x. Now we're going to approach negative 3 from both sides. So go back to the table, and it's already set, sorry. And what we would do is just change those independent x values since we already have it set at table set ask. So you might want to try it, you know, if you're not comfortable using your calculator, but I'm just going to go force feed them to you here. 1.259 and 1.180. And limits, I'm going to be honest with you, I'm a huge lover of calculus, and I absolutely love derivatives, and I really like integrals a lot. Like, they're almost twins to me, but I do like one a little bit more than the other. I'm going to tell you that I kind of consider limits the least interesting, but the most necessary of the 3. It'd be wonderful if I didn't have to cover them first, but I do. Just you'll understand why when when we get to the other two that I really needed to start with limits, but it's kind of a bummer that we start with the least interesting. But if you watch some of those flip grids, they did say it gets very applicable and very interesting, and that is the truth. It really does. So it says, based on the values, what happens as I approach -3 from the left-hand side? So as I'm coming in from the left-hand side of -3, I seem to be at this 1.167, same as from the right side. So I seem to be this 1.167. It shouldn't surprise you that that's the decimal version of 7/6 rounded to 3 decimal places. Because remember the location of that hole on the graph. So let's pop back here to that graph, shall we? Let's pop back here. As I came in, so you'll notice that my table is really corresponding to my visuals on the graph. So we don't need to answer that one. All right, so last step. Now we're going to approach 3. It says complete the table below and perform the numerical blah, blah, blah. I shouldn't say blah, blah, blah. I don't want to negate its importance. It's just that number crunching is not my favorite thing to do. So I will go hand you, by the way, in this class we have a 4-pronged approach to calculus. We do graphical, numerical, analytic, which is algebraic, and we are wordsmiths. So we call it the GNA approach. The numerical is probably the weakest of the 3, but it does help. If the other ones are failing you, you could always do what I call a creeper, and it means just kind of start creeping up with numbers if you can't get it the other way. So that's 5.02, 5.2. And this one was 8.667. 8.667. Over here we had a -4.988, and over here we had a -4 point. And I'm not going to finish the chart because we want to see what's happening and what we guess is happening as we approach 3 from the right-hand side. So I'm coming in at 3 from the right-hand side, and take a look. Coming in from the right-hand side, and I'm approaching 3, right? And then I'm going to be coming in, let's come in from the left. And let's also approach from the left. Now this is what I call a split personality. You might say, well, it looks like it's approaching 5, and then this one's -5. But remember, what it means is there's a split there. One's going up and one's going down. All right, and rational functions, they can't just for a rational function, if you remember your algebra, you can't just do that and then like that. You know, there's either an asymptote or a hole there. Those are the two issues. So my issue right here isn't that I'm arriving at the same place. I'm going up on one side and down on the other. So this one, I'm going to guess -infinity. Now on your calculator, maybe try 2.9999999, whatever it allows you to. Actually, let's go do that really quick just so you can see it. So, just a second. I'm not fluid with these button pushes because it's been so long. It's weird. It's not my muscle memory isn't as great as it used to be. So what were we creeping in on there? 3, right? So let's try 2.99999999999. Remember, we are creeping up on it. Oh, it gave me an error. It's saying, I'm going to use 3 and there's an issue at 3. So let's see if it allows fewer. I think I just did too many. Let's see if it allows that many. -5 e to the 7th. That's -5 times 10 to the 7th. It's way down there. And that supports my -infinity. Okay, so notice what we're getting here is when we get those infinities as our, I'm going to go back down here, those infinities from our table or our graph correspond to the vertical asymptotes on the graph of the function. So if you were ever to get limit as x approaches 17 from the right of h of x, and you decide it's -infinity, you've got an asymptote at 17, and your function, whatever it might look like, is heading that way. So when we get these infinite limits, it means whoop, asymptotic behavior, whoop. All right, so let's practice a little bit here. Oh, limit existence theorem, sorry. This is the definition of a limit. So let's talk about what makes a limit exist. All right, so let's write a limit exists. And I rarely do notes this long, guys, but it's just kind of like 3 small things, so just lumping it all together. If and only if, that's what this symbol means. So a limit exists if and only if the limit, as we come in, add a number, I'm going to call it A, sometimes we call it Z, from the left. So it basically means hop on the road from the left. So maybe on this guy, I'm going to approach -1. So let me go to a blue pen here. Just 1 second. I don't change my black to blue. So I'm going to approach -1 from the left. And it looks like I'm up at 1. I'm going to approach -1 from the right. It still looks, do you see how both roads are leading to the same place? If they're both leading to the same place, that place might not exist. There might be an open dot there. Maybe it's Jimmy John's. But we're meeting up for a date and we're both in the parking lot. We did not know that rioters burned Jimmy John's down last night. So we're there. So it's where you are, even if that does not exist. So the limit, as we approach from the left, has to equal the limit as we approach from the right of the function. But furthermore, like, they can't both be infinities. So we're going to refine that a little bit. Like, you might say, well, as I come in at 2 from the left and come in at 2 from the right, they're both infinity. So I'm going to say my limit's infinity. Actually, we have to equal, because you can't grab, you have to be able to grab it. Okay, you have to be there. These 2 people going on their date will never meet. They can wave at each other, but they will never meet up. These guys can meet up. So let's call it equals some k, where k is a finite number. Okay, so k is a finite number. Infinity is not a number. It's a destination that can't be reached. All right, so let's approach 2 from the left. So we're approaching +2 from the left. We're heading to the moon. Let's approach +2 from the right. We're heading to the moon. The y value there actually does not exist. Does the limit exist or not? And the answer to that is no. And it's because I'm not arriving at the same place. We're getting, for example, infinity plus 2 is still infinity, and I would say that those are the same. So infinity is not a quantitative number, it's a destination. So that's a no, because we're heading to the infinities. Now, this graph, if we approach 2 from the left, there I am at Jimmy John's. 2 from the right, there I am at Jimmy John's. Here's Jimmy John's, located up at 2. But f of 2 is actually equal to -3. That does not matter. Remember what I said. As long as you're there, right? Even if the place doesn't exist, that's the limit. The limit as I came in from the left equal the limit as I came in from the right equal a finite number. So yes, and you would write that. Limit x approaches 2 from the left of the function, this is function f again, is equal to the limit x approaches 2 from the right of the function, which actually equal a finite number. All right, last up with these. Hopefully you're getting this. Is kind of easy, I think. Graphical is pretty easy for limits because you just hop on and walk the road. Walk towards 2 coming in from the left-hand street. Where are you? Again, limits are y values. I'm at 3. Approach 2 from the right-hand side. Again, it's from this direction on the graph. As x approaches 2 from the right-hand side of it, where is my f of x? It's at I am at -3. The function's not defined there. F of 2 is the y value there. That's f of 2 is 3. Does the limit exist? No. The left and the right, we did not meet. I got bad directions. I thought Jimmy John's was up here, and it was actually Papa John's was what my date thought we were going to, and we did not meet. All right? So Hopefully neither one has COVID. No. And you would write limit. You'll see my limits get really sloppy in this class because more in Calc 2, because I write them so much. Limit as x approach 2 from the left does not equal limit, and I'm doing something on purpose here. This approaches 2 from the right. That, notice I'm getting fast, I'm getting sloppy, and you will lose points. So I want you to think about what is it about this that would cause me to go -1. If you did it on a test or even on the AP exam, you won't earn what's called a lot of times a notation or proper expression, mathematical expression. And it's not because my limit is so messy. To be honest, I'm a reader for AP Calculus, and I've read thousands of exams, and they really say try to read with the kid. If they have bad handwriting and you're 90% sure it's a 7 and it's supposed to be, I'm sure that person's trying to write limit. That's not the issue. I forgot the subject of the sentence, and that matters. Again, you write in English, you know, I don't know, tastes good. It's like, well, what are you eating? I really want to know. I want one too. Anyway, based on what you have seen so far. Does she always talk this fast? No, I'm just trying to cruise through this first part because it's not the super important stuff about limits. So based on what you have seen so far, does f of a have to be defined? Okay, what does that mean, be defined? There are 2 ways to not be defined. There's either an open hole there, or you just can't get there because you're going up or down forever in order for the limit to exist. Okay, so think about that. Does it have to be defined? And if you've heard me talk about that restaurant, the restaurant does not have to be there. So it says draw and explain 2 different graphs. So the answer is no, it doesn't have to be. Draw and explain 2 different graphs. Usually if we were doing this in class, so if you hadn't been doing this distance learning or on the year 8A or whatever it is, I'd be walking around and looking at graphs and saying, well, here's what some people did. Most people for this one over here do the restaurant thing. I'm not defined here at A, but I certainly have a limit. Maybe it was 3. We're at 3, right? This one over here usually has some different, and think about it, a lot of kids will do that same restaurant analogy. They'll say, well, you're there and you're here and we didn't meet, right? And in both cases, f of a is undefined. Think about what if I walked around the room with the kids who are in class today. Think about what some other kids might have drawn, and maybe you did as well. And a lot of times what they'll do, at A, is have asymptotic behavior, either to the same infinity or opposite infinities. All right, the limit doesn't exist there. Okay, so undefined, no limit, undefined, no limit, undefined, limit. All right, so below is a set of tables of an exponential function. The reason that function family has been given to you is because it matters. Because you only have a small screenshot, a tabular view of the function, you really don't know what it looks like, but if it's exponential, you do. All exponential functions, right, are either exponential growth or decay. They all have a horizontal asymptote, right? Not always 0, but. So they look like that. So the first thing you ought to do is decide, well, is this exponential growth or exponential decay? Well, look at what's happening as we approach negative infinity. We're going up. Which one of these 2 over here, as I approach negative infinity, am I going up? As x approaches negative, so I'm going at the graph this way. It's this guy. All right, so I'm looking at sort of that blue function family. That just gets changed, they're of the form a times b to the x. This base controls how fast it grows. This a controls basically the like the stretch of it, that type of thing. So let's go take a look here. As I approach negative infinity, I numerically look like it. You might say, well, how do you know it's not 600? Because exponential functions, I know what they look like. Limit as x approaches negative 3. What does that seem to be arriving at? Now take a look, because I know what an exponential function, you might say, well, it's 9. It actually is. And you might say, yeah, but right to the left of it is 3, but it's not immediately. So because I know this exponential function is, hey, sorry, I was just saying hi to somebody who knocked at my door. Anyway, because I know I have this exponential function up here, I've lost my little handprint that allows me to go to my highlighter. Where did it go? Oh, well. I'll go red on the blue graph. So as I approach -3 from the right, at -3, I'm up here at 9. But because I know what exponential functions look like, and they're continuous, they don't have holes or asymptotes, vertical asymptotes, I can definitively say I will be at 9, but only because of that word exponential function. Linear would be the same way, by the way. If I ask you what's the limit as x approaches 2, and you might say, well, you're only telling me from one side. Well, because it's a line, I know I arrive at the same place from the left as from the right. Limit as x approaches 1, same thing. It's going to be 1.5 because it's going to be f of 1, just because I know that's an exponential function. And then as I approach infinity, I'm approaching an asymptote. So you might guess the asymptote's 1. I think that's a good guess. Or you might guess 0. Again, it's an estimate. So I'm going to put 1. I'm going to say, I think it's got 1 up there at 1. All right, so this would be kind of the same thing, but notice we've got these undefined parts of our graph, and because it's a rational function. Remember what that is. It's some polynomial divided by some other polynomial. They have issues where there's asymptotes. So where there's vertical asymptotes, they also have issues where there's what we call holes in the graph. So 2 issues for rational functions. You need to numerically guess at what they are. My guess for this, asymptote, because look what's happening to the left and the right. I'm going up to the left, way down to the right. My guess for this one is there's a hole in the graph. Because I'm approaching the same value, 0.3 repeated, 0.3 almost repeated. I feel like there's a hole in the graph at 1/3, or 0.3 repeated. Because I'm arriving at the same place, but they're telling me it's not defined, right? And it doesn't look like it's asymptotic behavior. All right, so let's approach negative infinity. Whoop, looks like I'm arriving at 1. Let's approach -1 from the left-hand side. It looks like I'm going way up at an undefined spot on a rational function. So I think at -1, I've got an asymptote, and I think I'm going, whoops, sorry. Anyway, I feel like I'm going to infinity. As I approach it from the right, I feel like it says estimate, right? Well, it says use it to find, but the title of the unit is estimating with tables and graphs. As I approach 2, I think it's at about 0.3 repeated, or 1/3. It's an estimate. As I approach infinity, what's this approaching? I don't know, I guess 1, right? Wouldn't you? What does that mean? That as I approach negative infinity, my y values are 1. And as I approach positive infinity, my y values are 1. What that means is I've got myself a horizontal asymptote. Okay? Must be, I don't know what the graph looks like, but as I go to negative infinity, my y values are being bound by 1. By the way, you can cross a horizontal asymptote many times as long as you eventually just sail on out there. All right, just a little nugget. All right, fast up. So with this graph, let's go do just a couple of these. I think we've got it, right? It does say if a limit does not exist statewise. So I'm just going to pop in and randomly grab 3 of them. If you were in class, I would have said, now take a couple minutes and do as many, 3 minutes and get as many of them done, and then we would check them. But again, that's what we lose here with the distance learning. So I just forgot what the heck I was approaching. I'm approaching -1 with no signage on it, which means from the left and from the right. So I go to my graph, back here, I hop on it, and I have x go towards -1 from the left, so hop this, and I'm approaching -1 on the x-axis, and where will I be? Okay, so if I was plotting dots, I would have -9 here, -5 here, -here, here. But I don't want to be this far away. I wouldn't even hop on over here. We want to see what's happening really close to -1 as we come in from both sides. And you'll notice both roads lead to the same defined value. But if there's an open dot there, both roads are leading there as well. So it looks like that. It's hard to read this off there. Is that dot at -1, -1? It is. So that would be a -1. And I challenge you to try some others. Let's go approach -infinity and see what happens to our y values. So as I approach -infinity, I'm not going to go way over here. I'm going to go, here. I'll jump the hole. I'll go like that. I appear to be approaching 2. So I have a horizontal asymptote. Limits as we approach infinities are horizontal asymptotes of graphs. It's going to be important later. For now, you just need to hop on the graph and say, oh, I'm at 2. All right, so last up for today, I think. I know you might say, she gives this many no's all the time, and not even close. All right, some days I don't even give any. But this is where, again, in different situations, I put you guys in some groups. And this is where you really get it, because it requires you to internalize everything and be able to create something of your own. Notice something like this could not be photomapped, right? What a great test question that would be, right? So first of all, let's talk about our domain. I have to have a solid dot at 0 something. I need to have either an open dot or an asymptote at 5, so we don't leave the domain of the function. The y value when x is 1 is equal to the same y value when x is 2, which is 3. So I've got 1, 3 and 2, 3 with some solid dots. So 1, 3, 2, 3. And again, you should try this yourself, but I'm continuous from 0 to 2. What that means is I don't lift my pencil. So from 0 to 2, do not lift your pencil, and from 2 to 5, and remember 2, 3, 4, 5, right here is 5. I have to end my journey at 5, but I can never quite get there. All right, let's talk about what happens. So I've got myself a couple dots. I know not to leave the domain of my function. I know not to lift my pencil on those 2 intervals, and now I've got a limit. As I approach 2 from both directions, because there's no signage on there, I have to be at 1. So as I approach 2 from both directions, I have to be at 1. All right, so let's approach 2 from both directions and be at 1. How about that and that? As I approach 2 from both directions, I'm at 1. That'll work. As I approach 5, I have to go to infinity. All right, now, it doesn't say anything about f of 0, right? But I was supposed to start this journey at 0, so you can start it anywhere you want. I think I'll just start mine right here. Because it had to be continuous, right? So I'm continuous from 0 to 2. Union to 0. Now take a look at what this is. It's open and it's open. Hey, that's got to be an open dot. But I have to be defined on the entire domain. So I think I better put a little dot somewhere else. And then it says as I approach 5, I have to go to infinity. So I know I have an asymptote there. So you might be tempted to just go, hey, there we go. You got to watch this. If y has exactly 2 zeros, it means y equals 0 twice. Well, y equals 0 on the x-axis. It means we need 2 x-intercepts somewhere along the way. Now, where do you want to create them? I don't really care. Again, this is a sample. I think I'll head down and go, oh, now I'm going to infinity. Now I have 2 zeros. And then what you should do with these always is double check. Go back. Am I closed at 0? Yes. Am I open at 5? Yes. Why did I do an asymptote, not an open dot? Because it said I'm going to infinity as I approach 5. Do I have solid dots at 1, 3 and 2, 3? Yes. Am I not lifting my pencil from 0 to 2, 2 to 5, but I'm open at 2? Yes. Is the limit as I approach 2 equal to 1? Yes. So I double checked it. All right. That's it for the notes. All right. And sometimes I'll ask you to submit pictures of the notes, so make sure you're taking them. Tomorrow is 5-ish minutes, if that, of just a recap and then some work time. I do believe the assignment for today is called an acrostic puzzle. It won't take you long, it's just graph reading. So it's just kind of a fun little way to get used to reading graphs. The main assignment is tomorrow, and you'll mainly have the whole hour to work on it. You have a good one. By the way, if you're wondering why some things are starred, I'll talk about that later when I haven't been talking for 40 minutes. Peace out, Girl Scout.